Let's discuss about this electron hole pairs. Okay. Okay. So previous class we have discussed about band gaps of typical semiconductors. We discussed band gaps of column 4 elemental semiconductors, column 3 and column 4 compound semiconductors, and column 2 and column 6 compound semiconductor. You can observe a variety of band gaps. Band gap decides characteristics of a material. Okay, whether material want to behave as a conductor or insulator or semiconductor, that is decided by the band gap here. For conductors, band gap will not be there. Sometimes very small band gap may exist, but semiconductors has got very small band gap. Band gap varies from zero point 0.1 to 4 electron volt for semiconductor. uh, among commonly used semiconductor, germanium has got very less band gap, 0.66 eV. And on other side, if you look at gallium arsenide, 1.42 electron volt. This is used in light emitting diode, LED manufacturing. Like that, we have gallium, antimony, and the variety of materials you can see here. Okay, you can refer to this Wikipedia so that you will find details on different materials and their band gap energies. Okay, let's move on to this electrons and holes. Okay, let us introduce the concept of electrons and holes, and we'll see how these electrons and holes, how the semiconductor conduct electricity with the help of the electrons and holes here. Okay, so as we said already, the bands can be represented by just drawing horizontal lines here. This bottom line here shows it's a maximum energy level for valence band. The line here shows it is a bottom energy level of conduction band. So this is minimum energy level of conduction band, maximum energy level of conduction band. These two are separated by the gap. Okay, forbidden energy gap or band gap. Okay, now let us see this how this current conducts electrons and holes move in this semiconductors. Okay, for semiconductors this Eg will be very less. So we are focusing mainly on the semiconductors instead of dealing with other materials. So you can see in semiconductors, valence band is completely full. You can see a lot of electrons. These small dots here in our representation shows an electron. So electron, at temperature, higher temperatures. If you look at the first point here from the band diagram before, we can see that semiconductors act as insulators at 0 Kelvin. These electrons filled a valence band and empty conduction band. There is a large number of states here. Okay, so in the beginning. Okay, so at 0 Kelvin, so this completely the electrons remains intact with the nucleus itself, close to the nucleus, or you can say it remains in the valence band, and this remains as an empty at 0 Kelvin. Therefore, at 0 Kelvin, semiconductor behave like an insulator. What happens if the temperature is raised? At elevated temperatures, electrons get excited. So that means electrons acquire temperature, thermal energy because of rise in temperature, and jump to the conduction band energy level EC. So this is the conduction band energy level. Once temperature is raised, electrons here which are present in the valence band, they get excited and they move into the conduction band energy level. Okay, this results in an electron hole pair. So for every electron that moves from valence band to the conduction band, there is an absence of electron here, which is called as presence of hole. The empty states are called as holes here. Okay, or absence of electron is called as a hole. So this leaves hole, the electron which has left this position, the white space, the dot here that shows it is an absence of electron. You can see number of white dots here. Of course, there are majority electrons here, but only few white spaces you can see here. That shows the electrons here in these positions as left, and they are moved into the conduction band. So this is called electron hole pair. So the electron what you see here, it has got a hole in the valence band. So the electron in the conduction band has a hole in the valence band. So this is called as a pair. Okay, so there is a, for every electron you see in the conduction band, there is an equivalent hole in the valence band here. So this results in an electron hole pair. Okay, an electron in the conduction band and a hole. Hole is nothing but an empty state left by the electron in the valence band. So as we told already, so the empty space left by the electron or empty state left by the electron is called as a hole here. Now let us see how this conducts electricity. So do you think here this conducts electricity here? Okay. Even though this conducts electricity, it will be very less, because once electrons are available in the conduction band, they're ready to move anywhere in the conduction band, because there are a lot of states, free states are available in the conduction band. Very few are filled with these electrons, what you are seeing here. Okay, and even you can see very few holes are present in the valence band here. That means there is enough room for electrons to occupy these holes, empty spaces here, and simultaneously there is again enough empty states in the conduction band for the electron to occupy. Okay, so again here the electron keep moving here and there randomly. Okay, it may not result in a large current, but a small or negligible current, it may result because of thermal excitation. So therefore, at room temperature or at elevated temperature, I mean 27 degrees Celsius. Okay, so you can see there is a electron current flow in the conduction band. There is a valence movement in the valence. There is an hole movement in the valence band. Therefore, this causes hole current in the valence band, and in the conduction band there is an electron movement. Therefore, it causes electron current in the conduction band. So here students should not get confused what kind of current exists in the conduction band and the valence band. Always hole current, holes keep moving in the valence band. So you can see the empty space. This empty space may be occupied by the next electron here, and this empty space moves maybe in the forward direction or maybe in the reverse direction. So that means the holes are moving here, or empty spaces are moving here. So when empty spaces are moving in the valence band, that results in a hole current. So in valence band the hole current exists, whereas in conduction band you can see number of empty states here. So electron keep occupying those positions, empty states. So electrons keep moving, so therefore it results in electron current. So in the conduction band there is an electron current, in the valence band there is a hole current here. And this current keeps varying depending on the type of semiconductor. We are going to discuss P-type and N-type semiconductor. You will get to know that in P-type semiconductor, this hole current which you are seeing in the valence band is going to be major. Okay, large current, hole current will result in the P-type semiconductor. And in the case of N-type semiconductor, which has got N-type semiconductor has got large number of electrons, so it gives you large electron current. Okay, but hole current is less in case of N-type semiconductor, and vice versa in P-type semiconductor, electron current is less. Okay, so the same phenomena is less likely to occur with an insulator. Can you tell me the reason why this electron hole pairing phenomenon, what you are seeing in the semiconductor, is less likely to occur in an insulator? Is there any specific reason? Any answer from your side?
EG is higher.
Pardon me?
EG is higher in.
Yes, exactly. Okay, EG is very large for insulator. So that means the electrons cannot move to the conduction band, because EG, the band gap energy required, is going to be very, very high. So this kind of phenomenon what we are seeing in semiconductor, the electron hole pair phenomenon, this is less likely to occur in case of insulator, but more likely to occur in case of semiconductor. Okay. Do you think this electron hole pair create any significant amount of current? This electron hole pair, as you know, that it's because of elevated temperature, maybe at room temperature. You are seeing this at room temperature. There are few electrons in the conduction band, and there are a lot of holes, again equal number of holes, not lot of holes, equal number of holes in the valence band, do you see any significant current out of this electron hole pair? Any question, any answers? Let me change a question like this. Do you think large current flows in a semiconductor due to electron hole pair? Think about this. See, because of temperature, you are seeing electron hole pairing happens here. My question is whether this electron hole pair, which results in an elevated because of elevated temperature or rise in temperature, do you think that current is substantial or the large?
The small current is there, sir. If doping is there, then it will become large.
You mean to say if you dope it, you will get large current?
It will change the property, sir. That's right.
Exactly, exactly. Okay, so in due to electron hole pair, the current that results is going to be very, very small. You know reason why it is going to be very small?
A number of spaces, sir. That
A number of
spaces, I mean holes and electron pair spaces that occupy.
suppose if I increase the temperature, assume that I have increased temperature from 27 to say 50 degrees Celsius.
Yes, sir.
In such case, do you think it results in any significant current?
It will increase from previous one.
It increases from previous. Any other
Increase.
increase? Yes, yes. Increase in from the compared to previous.
Yes, sir.
Okay. Any other answers from other students? I don't know. What's your name?
Sushant Gupta.
Sushant, you are saying that rise in temperature increases electron hole pair, and you are saying that current also increases. Am I
A
right?
little bit increase. Yes, sir. Because at the surface of the electron will get excited.
Okay. Okay. So, any other answers you have? Have you come across the term called as generation and recombination?
Yes, sir.
Right now, what we are discussing is electron hole pair generation. Okay.
Yes, sir.
What do we mean by recombination?
They occupy the same space, whatever they left.
Exactly, exactly. So electrons, what you see here, these electrons in the conduction band has been created because of rise in temperature. The electron left its position here, and it has moved to the conduction band. Now here, how long this electron can stay in the conduction band? According to Pauli's exclusion principle, electrons will have to occupy lower energy states, even though these electrons has got excited and they are moved into the conduction band. Uh, After some time, they have to come back to its original state, because electron will tend to occupy always the lower energy states, because they are having a close attraction towards the nucleus, protons. Therefore, these electrons here, what you are saying here, it has to come back to its original position. Not every electron, but a few of them will come back to its original empty state here. May not be this exactly the same space here. It may come to, maybe some other space may be created here, and this electron may come back and occupy that space here, right? Empty state here. This process is called as a recombination. So you have understood the two key terms in today's class. One is electron hole pair generation. Because of increase in temperature, electron moves into the conduction band, and it creates an absent empty space in the valence band. This is called as a hole. And after some time, this electron will come back to its normal state, the empty state which has created earlier, and that process is called as a recombination process. Okay. Now here, when the temperature is raised, this current due to the electron or current due to the hole remains almost constant. Okay, it doesn't increase, it doesn't even decrease also. Reason behind that is, as we told, that electron hole pair is because of rise in temperature. As temperature keeps increasing, more and more electron hole pairs are created. At the same time, you will also see there is again recombination also. So generation and recombination both will be balanced, and finally you will see a constant current flow in a semiconductor. Okay. So I hope you got some idea about hole current and the electron current here. Okay. So generation and recombination. So both will balance each other, and the net current flow in a semiconductor is going to be constant. Maybe few milliamperes of current, small microamperes of current you can find in the semiconductor because of elevated temperature or due to the electron hole pair. You may not see significant amount of current in the semiconductor because of electron hole pair, because there is another process called as a recombination process where electron will come back to its original position or empty space and it gets filled. Okay. So due to that, this electron hole pair generation and recombination will balance each other, and as a result, net, if you look at an average current flow, is going to be a constant in the semiconductor. Okay. Okay, let's move to the next thing. The intrinsic semiconductor. What do we mean by intrinsic semiconductor? Intrinsic semiconductor, it's a perfect semiconductor crystal, what you are seeing here, with no defects or impurities or dopants added. We are not going to add any additional materials or substances to the pure semiconductor. So it's a purest form of semiconductor is called as an intrinsic semiconductor without adding any impurities or dopants. Okay. So you can see here the crystal lattice of silicon is shown here. So this small circles here shows a silicon atom. Okay, this is a crystal lattice of silicon we have taken here. Okay, and this bonds you can see the lines here. What you are seeing here, they represent electron. So each line here represent an electron. So that this silicon atom has formed a covalent bond with this particular silicon atom. This bond is called as a covalent bond. Covalent bond is formed because of sharing of electron. This atom shares one electron and this atom shares another electron. This forms a covalent bond. So these are the outermost, the electron. They forms the covalent bond, whereas inner electron, they don't participate in covalent bonding. Okay, so you can see likewise, there are this particular silicon atom. You can see it has formed bond with this particular silicon atom, and this since outermost orbit has got 4 electron with each, with this atom will share one electron with each silicon atom, and it forms a covalent bond. Okay, now since electrons and holes are created in pairs, we have seen in the previous electron hole pair formation because of elevated temperature. So they are created in pairs. That means for every electron in the conduction band there is an hole in the valence band. The concentration of both will be equal. Okay, as you have seen in the previous diagram here, the concentration of electrons in the conduction band will be equivalent to the concentration of holes in the valence band. Okay, so the both electron and hole pairs are created in holes are created in pairs. The concentration of both are going to be equal. So let us say this small n indicates electron concentration and small p is represented as hole concentration. That will be equivalent to a constant value Ni. Ni stands for intrinsic concentration. Its unit is per centimeter cube or 1 by centimeter cube. Okay, so now we will see that how exactly the electron hole pairs are created. In the previously we have shown in terms of the band diagram how exactly electron hole pairs are created. Now it's a time to think how this electron hole pairs are created. Because of rise in the temperature, what happens in the silicon crystal lattice is the electron here, suppose if electron which was earlier here, so because of rise in temperature, this electron will become free and it has moved to this place. So now this empty position, you can see here there is a line missing here that shows it is a hole presence there. There is no line means there is a presence of hole. So the hole has been the empty state you can see between these two silicon atoms here, and that made electron free here. This has moved to the conduction band now. Okay. So this hole now will not be constant, because see there may be another electron here which is here that may get attracted to this empty space here. That's what you are seeing here. Okay, so this electron here which is line, this line shows an electron here, this may get attracted to the empty position, and you can see that the empty position has moved to this here which is shown here, and this electron get occupied filled with this state. Now this bond has become the covalent bond, and here there is an absence of electron that becomes a hole here. Likewise you can see here the holes are moving. Okay, so this hole may attract another electron here that may come and fill its position, and the electron the covalent bond may be formed and another empty space is created like this. So like this, this in the entire crystal lattice, the holes keep moving or empty space keep moving, and simultaneously this electron also may get occupied by the empty spaces, and electrons also keep moving. Okay. So this dot here, the block dot shows an electron here, and this absence of this line, blue line, shows it is a presence of the hole or empty space. Okay. Now question for the discussion here: if we elevate temperature, will Ni increase or decrease? Any answers from your side? If temperature is raised, intrinsic concentration increases or decreases? At same time, I will ask another question to you all. Recall that a non-zero temperature, that means the temperature is very large, electron hole pairs are constantly being created. Why is not the carrier concentration?
Sir, it remains same.
You mean for what is the answer for first question?
Sir, it should remain same because we are not doping, sir. We are not adding any impurity or any other material in it. We are just increasing the temperature. It's changing its position from one place to another, from conduction valence band to conduction band.
So what we are trying to say is Ni is nothing but intrinsic concentration. If you look at this Ni equation, which is equal to N electron concentration and as well as hole concentration. And the question is, if temperature is raised, whether Ni increases or decreases?
Sir, it should remain same, sir, I guess.
So you are increasing. Earlier you said that as temperature increases, electron hole pairs to some extent it increases, right?
No, sir, I didn't say this.
Sushant has answered, it seems. Okay. Okay. So in my view, in my opinion, so this when the temperature is raised here, obviously see the rise in temperature. What happens here? The bond more and more, this covalent bonds will break, right? Okay. Suppose here you are seeing for say 27 degrees Celsius at room temperature, this particular bond has been broken, and if I raise the temperature, another covalent bond will break. That releases again electrons, and the empty space is created here. Likewise, in the entire crystal lattice, because of rise in the temperature, more and more covalent bonds will start breaking, and that will create the more empty spaces, and as well as electrons are made free and they move into the conduction band. So obviously the answer for the first question is, if the temperature is raised, definitely Ni will increase. Ni means it is both electron concentration and as well as hole concentration. So both concentration of electron and hole will increase when the temperature is raised. But recall the second question here. When the temperature is increased, electron hole pairs are constantly being created. Carrier concentration, do you think carrier concentration is not, why is not carrier concentration constantly being increasing? Reason is, as we told already, recombination process is there. So for every carrier generated, there will be again there is a recombination process. Due to that, the carrier concentration, it doesn't increase, it maintains a constant. Okay, understood the second question here? For second question, the answer for the second question is, carrier concentration will not increase because of increase in the temperature. Okay, overall I am saying here. Okay, so because of electron hole pairs, there is another process called as a recombination process. So that recombination process and EHP both will balance each other, and you don't see any increase in carrier concentration. Okay, but as a Ni, if you look at here, number of electrons and number of holes will increase. But again, EHP and as well as the recombination process together it will balance, and carrier concentration, it will not increase, it maintains a constant. Okay. Okay, let's look at this intrinsic carrier concentration versus temperature graph. Here you can see that there is y-axis represents intrinsic concentration, okay, which is Ni per centimeter cube is going to be the unit, and x-axis you can see which represents again temperature, and look at the unit here, it is 1000 by temperature. Reason is the relationship between Ni and the temperature is exponential. To make this the temperature and this Ni relation very small, we are going to divide this 1000 by the temperature. Okay, otherwise these lines what you are seeing here may not look like a straight line. It's very difficult to plot under this region if you plot directly the temperature here. Therefore, since Ni and temperature, they are exponentially they are related to each other, So we need to do some mathematical manipulation here so that these lines are available in the visible range. Okay. So this is what the x-axis. X-axis is nothing but it's not just a temperature scale. It's 1000 by temperature per Kelvin. Okay, that's going to be the x-axis. Okay, y-axis already we said it is intrinsic concentration in per centimeter cube. And also observe here, though temperature has been divided by 1000 has been divided by the temperature. So here you can see the exact scale. So this is 250 Kelvin, 300 Kelvin, 400 Kelvin, and as well as 500 Kelvin. And we have shown here the temperature dependence of semiconductor materials with reference to the the intrinsic concentration. We have shown for three materials. One is germanium, silicon, and gallium arsenide. At 300 Kelvin, you can see that the intrinsic concentration for germanium is 2.5 into 10 to the power of 13 per cubic centimeter, and for silicon it's less compared to germanium because of it's 1.5 into 10 to the power of 10 for silicon, and gallium arsenide you can see it is very less compared to silicon, even 2 into 10 to the power of 6. And do you think all these band gaps are same? Though intrinsic concentration for germanium you can see which is large. And what is the band gap of germanium? Exactly 0.66 electron volt. That is the band gap of germanium. So germanium has got very small band gap compared to silicon. Silicon has got 1.1 electron volt band gap. So and gallium arsenide, it's going to be large compared to the silicon. Anybody remember what is the value of band gap value of gallium arsenide? Previously we showed that, right? Yeah. For gallium arsenide it is going to be 1.42 electron volt. So this is the gallium arsenide, and look at the silicon, it is 1.12, and germanium you can see it is 0.66 electron volt. Okay. So because of germanium has got small band gap and its intrinsic concentration is very large. Okay. Whereas silicon has got the moderate band gap which is 1.1, its intrinsic concentration is 1.5 into 10 to the power of 10. And the band gap of gallium arsenide is very large, so it is its intrinsic concentration is 2 into 10 to the power of 6. So when the equilibrium concentration, when the carrier concentration is at equilibrium, the rate of EHP generation is equal to the rate of EHP recombination when the temperature is at equilibrium, when the carrier concentration is at equilibrium. Okay. So both generation and recombination will become equal. The equilibrium concentration is higher at higher temperatures. Okay. So that Ni keeps increases at higher temperature. As you can see for germanium, at higher temperature Ni keeps increasing, and same thing with reference to even silicon also. At 500 Kelvin you can see the value is going to be very large, and for gallium arsenide you can see that it's very large. As temperature keeps decreasing, Ni keeps decreases. Okay, the explanation is given here. Okay, so equilibrium concentration is higher at higher temperatures. That means Ni concentration is increases with the increase in the temperature here. Okay, so that's about the intrinsic carrier concentration. Okay, next let us see the other type of materials called as extrinsic or doped kind of semiconductors. So there is another way to generate carriers in semiconductors is by introducing impurities into the crystal structure, crystal lattice. If you add an impurity, then you can increase the carrier generation here. So this process is called as a doping. So doping involves adding column 5 elements or column 3 elements when forming the silicon crystal. During the formation of silicon crystal, either you can add column 5 elements of the periodic table. Column 5 elements are pentavalent, and or column 3 elements also can be added, which are trivalent, impurity elements. That creates different types of semiconductors. Let's see now what happens when we add column 5 elements. Column 5 elements are also called as a dopant atoms. Example of column 5 elements are phosphorus, arsenic, and antimony. So they are all column 5 elements which are pentavalent in nature. In the outermost orbit you see 5 valence electron in this material. So when we add this to the silicon crystal lattice during the formation of silicon crystal, so it increases the electron concentration in the conduction band. That means these are pentavalent in nature, therefore it increases the electron concentration in the conduction band. So these kind of impurities are also called as donor impurities, and type of semiconductor is called N-type semiconductor. You can also create another type of semiconductor called as a P type of semiconductor by adding an acceptor impurities. So acceptor impurities are nothing but they are the column 3 elements of periodic table. Example is boron, aluminum, gallium, indium. These are the example of column 3 elements. They are trivalent in nature. They are having 3 valence electron in the outermost orbit. So that means for every acceptor impurity added, it creates an empty position in the valence band. Okay, so it increases the hole concentration in the valence band. So therefore, in the p-type semiconductor, the hole concentration is very high. In case of n-type semiconductor, electron concentration in the conduction band is very high. Okay. If you look at the crystal lattice of silicon, this is an phosphorus, which is a pentavalent impurity added. So this phosphorus forms covalent bond with adjacent silicon atom. Since this phosphorus has got 5 electrons, as we have shown here, it has got 5 valence electrons in the outermost orbit. So 4 of them forms a bond with the adjacent silicon atoms or neighboring silicon atoms, and 1 electron which is vacant. Okay, so this electron is in the conduction band. For every phosphorus impurity added, it creates an 1 electron in the conduction band. Okay, so you can see in the energy diagram also, we can show this by plotting energy diagram by plotting this valence band at the bottom and conduction band. By adding an impurity, you are creating an empty state here, which is towards the vicinity of the conduction band. So these empty states, these electrons what you are seeing in the donor state which is near to the conduction band, they can move easily to the conduction band. Okay, so since there are a lot of empty states here, the electron which is here, this falls in the into the vicinity of this conduction band, which is called as a donor state. Okay. Next is to make a p-type semiconductor, we need to add the boron. Boron is trivalent in nature. You can see 3 valence electrons in the outermost orbit. So 3 of them forms bond with the neighboring silicon atoms, and 1 electron from silicon exists, but there is no electron to fill this position. Okay, so therefore this empty position is created because of the boron or impurity element added here. So for every boron element impurity added, it creates an empty position here. From the band structure point of view, if you look at by adding the trivalent impurity, you are creating an empty position which is close to the valence band here. Okay, so this empty position is because of adding an impurity element such as boron. Okay, so this is an energy band structure of p type of impurity here. Okay, so let's see the next thing with more details. So we have discussed so far the silicon crystal, and it's which has a band gap, and there are no energy states. Where there are no energy states in the in between, so you are creating some energy states. Example, you can see here at the bottom, by adding the pentavalent impurity, we are going to create here donor energy levels. You can see at the towards the vicinity of the conduction band. So you can see there are electrons you have created. These electrons are due to the donor impurities added here. So adding a dopant introduces energy states within the band gap. So adding pentavalent impurity, it creates, it introduces the electrons, okay, near the conduction band here. Okay, so this is at 0 Kelvin. What you are seeing here, at 50 Kelvin, you can see that this electron has got sufficient energy. They get excited and move into the conduction band here. Since conduction band has got a lot of empty states here, this electron can easily move into the conduction band. So though the electron, earlier we have discussed about electron hole pair, when the temperature is raised, we have seen the electron moving from valence band to the conduction band. That's called electron hole pairing. Addition to that, by adding the donor impurity, you are going to create an electrons or a dopant element. This creates an electron here, and any excitation here for the n-type semiconductor, these are all donor impurities that electron keep moving into the conduction band. So reverse, you can see in the case of the p-type semiconductor, at 0 Kelvin there is an empty state which is close to the valence band, and these empty states are unfilled here. When the temperature is raised, so these electrons which are present in the valence band, they acquire energy, they get excited and they move into these empty states here. And the moment they move into the empty states here, that creates a lot of empty positions in the valence band here. That means by adding the donor impurities, you have created a lot of electrons in the conduction band. By adding the acceptor impurities, we created a lot of empty positions in the valence band here. So these are the two different types of the semiconductors which are very important. Okay. So with more details we have shown here for the donor type of impurity. This is at 0 Kelvin. You are seeing here the electrons which are in the forbidden gap, which is the EG region. Okay, so any excitation, these electrons keep moving into the conduction band here. Okay. So any questions about that before we move on to the carrier concentration? I hope you understood the intrinsic and extrinsic materials. Okay.
Yes.
Okay. Any questions you have before we stop today's class? Next class we'll talk about the direct and indirect semiconductors. Okay.